All right, I'm going to make a small correction here. This should have been f of r theta, dr d theta. And let's make f of r d theta just 1. Let's find the area in our integral here. Whoops, I forgot the 1 to 1 plus cosine theta. Started to rewrite this, and I forgot one part of my integral here. So let me rewrite this in properly here. So we're going from 1 to 1 plus cosine theta. And since we're going to find the area, we'll work it across r dr d theta. So we'll do our first integration in terms of r, which will give us r squared over 2, evaluated from 1 to 1 plus cosine theta, d theta. And we'll have to do that integral in terms. So let's do our substitution in. We're going to get, I'm going to bring the 1/2 outside for right now. And so we're going to get 1 plus cosine theta squared minus 1 d theta. Right, we bring the 1/2 out completely. And we'll get this. All right, so let's square this. So that's 1 plus 2 cosine theta plus cosine squared theta minus 1 d theta. Evaluated from negative pi over 2 to pi over 2 with a 1/2. And then let's see, was minus 1. So 1's cancel out, so we're going to get 2 cosine theta. And we're going to use our power reduction rule. So this will be 1/2 cosine 2 theta plus 1 d theta. Evaluated from negative pi over 2 to pi over 2. Whoops. I zoomed out here. Let me get back in. Why is it not letting me zoom back in? There we go. There we go. That fits back in. Get my 1/2 back out here. All right, so we'll do this integral. So it's 1/2 sine theta, 2 sine theta, all right, plus 1/2 sine theta, or sine 2 theta, sorry, plus 1 plus theta. Right, because this will go up to sine theta, and this goes up to sine 2 theta with the chain rule 1/2 coming back out. And this will be evaluated from negative pi, whoops, bigger parentheses here, evaluated from negative pi over 2 to pi over 2. So that means we're going to have 1/2 2 sine pi over 2 plus 1/4 sine pi plus pi over 2 minus 2 sine negative pi over 2 minus 1/4 sine negative pi minus pi over 2. So we're going to get 1/2 2 plus 0 plus pi over 2 plus 2 minus 0 plus pi over 2. seem to be missing a fourth somewhere. Let me see. Oh, wait. This 1/2 here multiplies to this. So this is 1/2 pi over 2. That's a pi over 4. And that's a pi over 4. So I'm going to get 1/2 4 plus pi over 4. Or pi over 2, because there's 2 of them. Let's see. And that gives me 2 plus pi over 4. Which is the area inside of that curve. All right, let's look at polar coordinates a little more closely and look at some boundaries and finding some limits that we can do within these. One of the things that we want to note is that if I'm going to do some region where I have some f of x, y, dx, dy, if I convert to polar coordinates, the same region is going to be f of, well, x is r cosine theta, and y is r sine theta, right? Those are our conversions that we've had. And then our dA element, our differential in area, becomes r dr d theta. So if we're moving from one Cartesian system to a polar system, we can change coordinates. An actual good example of this would be, let's look at the region of e x squared plus y squared dy dx. And we're going to bind this by the region where it's going to be the upper half circle. So y is going to equal 1 minus x squared. Where we put ourselves into the upper half circle of this here. So if I draw this out, let's draw out the region we're bounding ourselves on. We're looking at the upper half circle, 1 minus x squared. And we're looking for the exponential x squared plus y squared. So what we're going to want to do is convert this to polar coordinates. In fact, it looks nice for polar coordinates here because this has a circular framing to it. So what we can do then is, if we think about what we're going to do from a polar standpoint, we're going to go from 0 to pi in angle and from 0 to 1 in radius. So we can do 0 to 1 for r, 0 to pi for theta. And then we can ask ourselves, well, what is this function now in r squared cosine theta and r squared sine theta? Well, if we drop this in, this is going to give us r squared cosine squared plus r squared sine squared, which is e to the r squared. And now our outer function will be r dr d theta. And so now we can integrate e to the r squared r. And I think if we want to look like e to the r squared r, if we look at this over here, let me just put e to the r squared r dr. If we're looking at this integration, then I guess how do we want to do this? We can do a u sub, where u equals r squared and du equals 2r dr. And if we substitute that back in, that's e to the u 1/2 dr, because the r dr is here. which means that this is going to be 1/2 e to the r squared d theta, and we're going to evaluate this from 0 to 1, 0 to pi. And if we evaluate this from 0 to 1, this is going to be 1/2 e minus 1/2, right? Because 0 will give us 1/2 from 0 to pi d theta. We can move the 1/2 out front, so we'll get 0 to pi e minus 1 d theta. And e minus 1 is a number. All right, e minus 1 is a number. So this will be 1/2 e minus 1 times theta evaluated from 0 to pi, which is going to be 1/2 e minus 1 times pi. And so we can convert a problem that's in Cartesian coordinates to cylindrical coordinates. All right, I'm going to do another example of some polar coordinates. I'm going to do example 5 in the book. We're going to look at a region bounded underneath a cylinder, or over top of a cylinder. It'll be example 5 in the book. And then we will continue exploring polar coordinates with a couple examples from the textbooks, and then we'll start talking about triple integrals.